In the previous video discussion on the strain gauge type force sensors, we described how the output from a full bridge, right, strain gauge sensor, this change in voltage when you apply a load and induce strain on this full bridge type configuration, that this change in voltage is still kind of small in the millivolt range. There's an input voltage here. Sometimes these sensors are characterized in millivolts per volt this way, and you should be able to see that that basically is calculated by the gauge factor and the amount of strain that you have. So, and remember that strain is for a given load. Go back and look at that third video. Now I just want to show you a typical type of amplifier that you can use to connect here, you know, on the output side of that bridge. This is a nice amplifier that I've used in the past for this lab. It's one made by Omega, which is now called Dwyer Omega. You can find it on the website, DMD465. A little bit more costly than the one that we use in the lab now from SparkFun. This has two different models, one for low frequency, out to low frequency signals about 3 Hertz, the other for higher frequency dynamic signals up to 2 kilohertz. And the couple key things about this guy also, this gives you an analog out. So the output from here, as you can see, you send right into some data logging or like an A to D converter. So this is purely an amplifier. You can connect your sensor up, right? All the different connectors. This amplifier has bridge excitation. You give it AC power here in the wall power, and you connect. You know that powers your bridge, and then you take the output signal, and it sends it into an amplifier, and then also a nice filter here. You can adjust these and so on. A nice little filter. And we used this one for many years. Very nice, low noise. Again, a little bit more costly. The amplifier that we use now in the lab is this SparkFun, which they call a quick scale. This is about an $18 device. It's SparkFun has put it on this little breakout board. You can connect it to Arduino, and the power for this guy comes from the Arduino bus, right? And then it powers the sensors. I'll show in the next slide. This is actually also for relatively low frequencies. It even says in their description and their data sheet for the NAU 78002, which this device is based on, is for low sample rate applications. It's like for making scales, low frequency vibrations that you want to measure. That's what we'll do in the lab. It's got a quick set of connectors here for connecting to the 4 leads from your sensors. I'll show you in a second. And you can't see it here, but green, white, black, and red connectors there. And you got to make sure those are connected well, as I'll mention in a second. Okay. So you set the sample rate here. For example, here is what the circuit configuration looks like. It says it's a kind of high resolution. It's got a high resolution A to D converter on here, right? 24-bit. You connect your sensor up as you see here, so it powers it and also takes in the signal, and then you send that to a local microcontroller, which then communicates with Arduino. You can send it a command to set the sample rate as to how fast you want to be taking data, and then Arduino can be asking it for that data, right? And you can go out to 80 Hertz, 320 Hertz, and so on. On the data sheet, I only saw the bandwidth designated up to 80. I don't know what the bandwidth would be for 320. But for the low frequency applications that we use in the lab, this works well enough. The way we configure it in the lab is we use it to instrument the strain gauges, to condition the strain gauges from these mini load cells. And this type of load cell is described in some of the previous videos that I've provided. But you can go to SparkFun here. It describes these. These are binocular type, as you can see here. We applied the loads here, and you can't see the wire. The wires go here. And I've done it this way because it's really easy to pull these wires out, and then you basically have to throw this thing away because you can't really fix them. This is a 500 range load cell, so you don't want to load it beyond that, half a kilogram. And in lab, you'll hook these up to this quick scale device. As you can see, the green, white, black, and red. Power it, connect it to Arduino, get it going, get some signals, do some basic measurements. We'll basically apply loads on here. This guy's fixed, cantilevered, known loads. Build a calibration curve. Basically what you want to do is, you want to know what you apply load and you build a calibration curve. So really what you're doing is like you're going to have known force here. Here this could be either voltage, or sometimes we just use the integer values that come out, like sometimes called the counts, but it'll be whatever this value is here that you're going to be measuring. And you can see if you've got a nice linear calibration, get your calibration constant, and then you can use this measure, whatever you measure here, you can convert to force. You'll build a simple little load cell, test it, and then we'll do some dynamic measurements with it. Maybe we'll actually attach a bungee cord here and a mass and measure dynamic vibrations with it, and so on. Okay. Now, of course, one thing to mention here in contrast with the previous analog amplifier is, a device such as this, right? All of the data that's going, to the Arduino is not analog. This is all sort of communicated via the I2C communications, right? So you're not taking analog data, you're taking these digital measurements, right? And that's, again, what we use here when we build our calibration. All right.